Here we go with our first line integral. 16.1 starts with vector fields. And a vector field is something that has a multidimensional input and a multidimensional output. So we have some famous vector fields like the gravitational vector field of the planet Earth. It's all pointing toward the center of the Earth. So when you look at the whole planet, it's a bunch of arrows all pointing toward the center of the Earth. So don't think of the vector field, well, locally, if you think of the vector field just in this room, they're all pointing toward the floor. But if you look at it globally, it's a little bit more exciting. There's vector fields from electrical current going through a wire, follows the right-hand rule. So you get that, you get the current going this way, the electromagnetic field forms like this around it. And here's the biggie, any gradient is a vector field. Because you take the gradient of a function, you get a vector function. You get a function that has, or you get a, it's called a vector field. You get a vector with a function at each coordinate. And the function at each coordinate has a multidimensional input. So that's a vector field. So here's the kinds of line integrals we're going to do a lot of, and they're the work ones. They're the ones that give you work. So here's what's going on. Here's my problem. This is the problem right here. Let me focus on this. This is our problem right here. And what we're computing is the work it takes to travel the curve C along a vector field that is x plus y, comma, y squared. So at every point in the xy plane, let's say the point 1, 1, at the point 1, 1, the vector would be 2, comma, 1. So you draw that vector at 1, 1, that's the vector for that point. So you draw a vector at every point. Well, we're not going to draw a vector at every point. It just look like solid ink. But if you draw a vector at a selection of points, you get a sense of what this looks like. So if it's two-dimensional, you can think of it as a wind pattern or something. And you're going to travel this curve. This curve is a piece of parabola. It's t comma square root of t going up to this point 4 comma 2. So it's t less than or equal to, or 0 less than or equal to t less than or equal to 4. C is the name of the curve, and it's the set of points. So it's these points, but R of t is this part, the vector part, which tells us how the points happen. It has orientation. It tells us how it's all laid out. So here's the work it takes. Here's the work that we do to get this thing to be a doable integral. So two big ideas with line integrals. One is everything in terms of t. Two is you want to get an integral you can recognize. Now look at this thing. This is x plus y from here. This is x and y. This is y squared from here. This guy here is dx dt. dx isn't just dx anymore. It's dx dt. So I get dx dt from there. That's a 1. dy dt, I get it from here. And that's the 1/2 t to the negative 1/2. And then you throw a dt on the end of the whole thing because that way this dx stood for dx dt. And dx dt times dt is the same as regular dx by chain rule. It's the same thing. So we got that. So this is everything substituted in. And look, it's all t stuff. And when you rewrite over here, when you rewrite it over there, you recognize this. That's a Calc 1 integral. That's not a tough integral. That's not so bad. So I have t times t to the negative 1/2, t to the 1/2. And that's added to another t to the 1/2. So I have 3/2 t to the 1/2. And we do the term by term and evaluate. That's a line integral. Now here is your homework problem. And it's a beauty. It's a beauty. One homework problem. It's right there. I want you to find this. It's the same integral. So it's that integral in that box that I had. That integral in the purple box right there. That integral, same curve C, but a different R. I'm asking for a different parameterization. If you look at this, this goes through, this point here is 0, 0. This point here is 4, comma 2. And if you try any other ordered pairs or just look at it, this is a piece of parabola as well. But this is the parabola where I let t be the y. The original was where the parameterization where I let x be the t. And I'm here to tell you, it doesn't matter which parameterization you choose. You will get the right answer. So we did this integral correctly. We got a 16. So that means you already know the answer to this problem. You do this problem until you get a 16. One homework problem. Dig it. See you when I see ya.